The Quantum Algorithm Revolution. Unveiling the future of computing through quantum mechanics in an era where computational power is the cornerstone of technological advancement. Quantum algorithms are emerging as a groundbreaking force poised to redefine what's possible in computing. These revolutionary methods leverage principles from quantum mechanics to solve problems that classical computers find intractable. The potential impact of quantum algorithms spans across industries, from cryptography and artificial intelligence to drug discovery and optimization problems, offering solutions at speeds previously thought impossible. As we stand on the brink of a new computing paradigm, understanding these algorithms becomes crucial for developers and researchers alike. Fundamentals of quantum algorithms at their core. Quantum algorithms harness the peculiar properties of quantum systems such as superposition and entanglement. Unlike classical bits which exist in either state 0 or 1, qubits can occupy both states simultaneously thanks to superposition. This dual-state capability allows quantum computers to process vast amounts of information concurrently rather than sequentially. Entanglement further amplifies this by linking qubits so that the state of one instantly influences another regardless of distance. Quantum gates manipulate these qubit states much like logic gates do with classical bits but operate under different rules governed by linear algebra and probability theory. These operations form the building blocks upon which complex quantum circuits are constructed. Algorithms designed using these principles often achieve exponential speedups over classical counterparts. For instance, Shor's algorithm demonstrates how factoring large numbers, a task critical for modern encryption, can be done efficiently using quantum computation. Superposition enables parallel processing capabilities not feasible with traditional binary systems. Entanglement creates correlations between particles enabling faster communication protocols within quantum networks. Interference, used strategically to amplify correct answers while suppressing incorrect ones during measurement processes. These foundational elements work together to create algorithms capable of solving certain types of mathematical problems exponentially faster than any known classical method. Pioneers in quantum algorithm development. The field has been shaped significantly by pioneers who laid down theoretical frameworks necessary for developing practical applications today. One prominent figure among them is Peter Shor, whose eponymous algorithm marked a turning point in cryptographic security concerns. Shor's algorithm demonstrated that factorization could potentially break widely used public key cryptosystems such as RSA. This revelation spurred interest not only in post-quantum cryptography but also accelerated investment into quantum computing research globally. Other notable contributors include Love Grover, who introduced an algorithm providing quadratic speedup for unstructured search tasks. His work established benchmarks against which subsequent developments were measured. Grover's algorithm illustrates how even modest improvements in efficiency can have profound implications when applied to real-world scenarios involving massive datasets common in machine learning contexts. Together, these early contributions set the stage for ongoing exploration into various domains where quantum techniques might offer substantial advantages over conventional approaches. Applications across industries. With its ability to handle complex calculations rapidly, quantum computing holds transformative promise across numerous sectors. In finance, for example, portfolio optimization becomes drastically more efficient due to enhanced modeling capacities afforded by quantum models. The pharmaceutical industry stands to benefit immensely from simulations enabled by quantum algorithms which accurately predict molecular interactions far beyond current classical limitations. This could revolutionize drug development timelines dramatically. Logistics companies may utilize quantum solutions to optimize delivery routes considering countless variables simultaneously, an application area ripe for disruption given existing constraints imposed by classical computational models. Cybersecurity faces both challenges and opportunities. While quantum decryption threats loom large, they also drive innovation towards robust encryption standards resilient against future attacks leveraging quantum supremacy. As each sector explores tailored implementations based on unique needs, cross-disciplinary collaboration emerges as key to unlocking full potential offered by this nascent technology landscape. Noteworthy examples of quantum algorithms. Several well-known quantum algorithms showcase distinct problem-solving paradigms applicable across diverse fields. Among them, Simon's algorithm addresses periodicity detection issues relevant especially within data compression technologies. Determining periods hidden within functions forms part of many cryptographic schemes, making Simon's approach particularly significant despite being somewhat abstract compared to other implementations. Variational quantum eigensolver, VQE, represents another pivotal technique useful primarily in chemistry-related computations aiming to determine ground states energies essential for material science advancements. VQE combines classical optimization strategies with limited-depth quantum circuits, allowing approximate yet sufficiently accurate results suitable for experimental validation purposes without requiring fully fault-tolerant devices. Each algorithm reflects specialized design considerations aligned with particular problem spaces, indicating broader applicability once hardware maturity progresses accordingly. Challenges facing quantum algorithm implementation. Despite promising theoretical foundations, translating quantum algorithms into functional implementations presents formidable hurdles stemming largely from physical implementation difficulties inherent in maintaining coherent quantum states. Decoherence remains one of the most persistent obstacles affecting reliability since environmental interactions tend to disrupt delicate superpositions, prematurely terminating desired computations before completion. Error correction mechanisms add complexity layers, necessitating additional resources, thereby increasing overall system requirements beyond what initial designs anticipated. Current noise levels restrict meaningful execution durations, limiting scalability efforts until error rates decrease substantially via improved materials engineering and control methodologies. Tackling these technical barriers demands sustained interdisciplinary cooperation, merging expertise spanning physics, computer science, mathematics along with advanced fabrication techniques required for stable qubit architectures. Advancements in error correction techniques to mitigate effects caused by decoherence and operational errors. Researchers continually refine error correction codes specifically engineered for quantum environments unlike those employed traditionally in digital electronics. Surface code implementations currently represent leading contenders, offering high threshold values relative to physical error rates achievable experimentally, thus forming viable pathways toward scalable architectures. Topological qubits propose alternative approaches capitalizing on non-abelian anyons exhibiting intrinsic protection against local perturbations, potentially reducing maintenance overhead associated standard encoding schemes. Developments in concatenated coding strategies enable hierarchical corrections addressing multiple error sources, simultaneously enhancing resilience against cumulative degradation risks present during extended operation cycles. While progress continues unabated, achieving sufficient fidelity remains challenging, demanding innovations targeting simultaneous enhancements across several interdependent parameters, including gate accuracy and coherence times. Future prospects and research directions. Ongoing investigations explore novel algorithmic constructs aimed at exploiting emergent phenomena arising from multi-qubit configurations, enabling richer expression capabilities beyond existing toolkits. Hybrid models integrating classical pre-processing stages followed by targeted quantum interventions aim to maximize resource utilization, ensuring cost-effectiveness amidst prevailing hardware limitations. Machine learning integration seeks synergistic relationships wherein quantum features augment traditional neural network structures, opening doors toward unprecedented analytical depth hitherto unreachable classically. Exploration extends beyond static problem formulations, embracing dynamic scenarios requiring adaptive responses mirroring complexities encountered naturally within biological organisms or social ecosystems. Such forward-looking pursuits underscore growing confidence regarding eventual realization of impactful applications, provided continued funding supports fundamental scientific inquiry alongside translational initiatives bridging academia-industry gaps effectively. Educational resources for exploring quantum algorithms for enthusiasts eager to delve deeper into quantum algorithms. Numerous educational platforms provide structured learning paths ranging from introductory modules covering basic principles up to advanced topics focusing on recent breakthroughs. Online courses hosted by prestigious institutions often feature interactive simulations allowing learners hands-on experience manipulating virtual quantum circuits, reinforcing conceptual understandings through practical experimentation. Open-source software libraries facilitate prototyping custom implementations, empowering individuals irrespective of formal training backgrounds to contribute meaningfully towards expanding collective knowledge bases collaboratively. Communities dedicated exclusively to discussing quantum computing foster vibrant exchanges, promoting idea generation, accelerating pace at which discoveries translate, practically benefiting wider audiences sooner rather later. Leveraging available tools combined with active participation ensures continuous growth, aligning personal skill sets closely with evolving trends shaping tomorrow's technological landscapes effectively. Conclusion: quantum algorithms signify more than mere academic curiosity. They represent tangible shifts toward redefining computational boundaries previously deemed insurmountable by classical means alone. By capitalizing on unique characteristics afforded by quantum mechanics, these innovative approaches open avenues exploring realms inaccessible conventionally, paving way for next-generation technologies transforming everyday experiences profoundly. Engagement with this rapidly advancing domain offers unparalleled opportunities, cultivating expertise highly valued within contemporary tech ecosystems, positioning participants advantageously amid unfolding digital revolutions driven increasingly by quantum-enabled capabilities.